Hello again. Let's start to our class. So let me check. Yes. Okay. So today we will continue about our Harmonic Control Arrays course. So this is our web page. So you can find presentation, the previous papers of this method. So we will go over this basic method. Actually, we will continue to learn about it. So there is a paper here. Actually, you should read this paper to start understanding this method. So actually, this is a good start. So let me start with the presentation. So we were doing this. We said that integral control is very important. Actually, not so many people are giving too much attention to this method. I mean, this integral control. But it's very, very useful. Actually, in industry, we use lots of controllers, PID controllers, and this integral control plays a very crucial role, I believe, because integral control is very useful for eliminating the error between the reference and the output at the steady state. In the transient state, maybe, I mean, things depends on other controllers like proportional control or derivative control, or of course there are many other controlling strategies to reach the reference level. But after that, to keep at reference level, you need a memory, because when you reach your destination, for example, you want 100 degrees at the output, and output is actually 100 degrees. So in that case, the error will be 0. So when it is 0, this controller only gets the information of 0. So with 0, you cannot do anything. I mean, you need to memorize the previous action. How can you do it? You can do it only with integral control, because in integral control, integrator, I mean, running integral, even if the input is 0, the output can be some number, like a memorized value, because integral keeps accumulating the input, just adds up the input until the current time. So it accumulates some value, and after that, even if you give 0 to it, it keeps the output value. Let's say the output is like 45 degrees, let's say, the gas pedal or something. Okay, it will be kept at 45, even if input is 0, and the car will go with 100 km/h, let's say. But proportional controller, for 0 input, will produce only 0 output. Or derivative controller, if it is 0 all the time, 0, 0, 0, the derivative of 0 function is 0. So it will not do anything also. So even if you have fuzzy control or something, maybe for fuzzy control or neural network control or something, even if you give 0 input, it will produce a certain output. But like a nonlinear function, I mean. It will be fixed value. For example, for 0 input, it will automatically produce 30 as an output. But it's fixed. For example, for 100, 30 or 45 is good, but if the reference changed to 150, let's say, now you need 60 degrees. But if you have neural net or fuzzy or something here, or proportional, whatever, or any nonlinear controller, it will be giving you only a certain value for 0 input. Because for 0, if it's a function, even if nonlinear function, it can only give you certain number. But you don't want that, because reference sometimes 100, sometimes 150, sometimes 50, sometimes 70, sometimes 0. Without knowing the reference, you cannot decide on the control value. So, but the integral control, in a very simple way, can handle this problem. Because if the error is positive, that means y is below r, y is positive. In that case, integrator output keeps growing because positive input. So it pushes the gas pedal. So if it is above the reference value, in that case, error will be negative, so it will kind of break because it will decrease the u value. So it will automatically find, if the total system is stable, it will automatically find the crucial input value at that time. So if a little bit positive, automatically adjust it. So automatically finds the necessary input value so that error is 0. When error is 0, everything is achieved. So if there is no new disturbance or changes in the reference, then it will automatically keep giving this value for you, even if E is 0. So that's why integral control is very, very nice tool for control. And in industry, it is used in the form of PID control. So maybe they are aware of this or not. I mean, for example, when you produce an air conditioner, in the let's say you are an engineer responsible of the fan speed. So you need to write a microcontroller program so that in that microcontroller program, you need to adjust the input voltage in the form of maybe PWM, pulse width control. So that the fan speed is a certain value. So for that, what do? You just implement PID control. So code is available because billions of products using this PID control. So you find this code segment about PID, you implement it in a C program, and it automatically works. What you need to do is just adjust the gains, PID gains, KI, KP, KD parameters. So you just try, and there are, of course, some methods for it also. Very old methods, new methods. So you can easily achieve it. And when you push the button, it automatically automatically turns and automatically reaches to that certain value, and you are done. You get your salary at the end. So everybody says, oh, wonderful job. So fan is working wonderful. So when I push the button, automatically it goes to 300 rotations per minute or 1000, whatever. So if the user wants to change it, you can change it. So actually, integral control is doing all these jobs, actually. Because if the error is positive, it automatically increases the voltage. If it is too much, decreases. So automatically, this is control, not the proportional gain, because proportional gain is only useful in the transient state to make things faster. So to reach the final value as fast as possible. But when it reaches there, when at this steady state, so it's totally useless. I say it's totally useless afterwards. What do you mean by useless? I mean, when the input is 0, proportional gain means Kp times E. E is 0, so whatever the Kp value, its contribution will be totally 0 here. So useless in the steady state, but very useful, of course, at the end. It's useful. Why? Because it makes things faster in the beginning. That's why it's useful. Because this integral control can be slow sometimes. Because if you make this Ki is very high, in that case, it can be it may be unstable. This system may be unstable. Why? Because when you have too much integral action, and if there is little bit delay in the plant, in the feedback loop, so before you know you are higher than normal, you can keep pushing the gas pedal. You can keep increasing the input because you are not aware that it's already above the desired limit, but you are not aware of it. You think that it's below because of the delay. It seems to be below, but actually it's already more than the reference. So you keep pushing. When you reach there, I mean, when you think you reach there, it's already way above your reference value. So in that case, you have to push down too much, but when you get 0 error, is already too low, actually, lower than the desired value. So if you keep doing this, you will be having growing oscillations. So it will be unstable. So you don't want this Ki to be too big, too large number. So to keep this, you can keep this low, especially for delayed system. But in this case, when you keep Ki slow, I mean small, in that case, it will be slow, very slow. So to compensate this, you can have a extra controller, only valid in the transient state, like proportional controller or derivative controller, so that your system is fast enough. So in industry, this system is used a lot. Many people maybe don't know how it works. It just works. I mean, you just need to adjust this Ki number. That's it. I mean, as a design engineer, as a control engineer, all you need to do is to choose this Ki. You don't need to do anything else. Because all the algorithms are ready for it in C or Java or whatever. So That's it. This is good. Our problem is actually, as you know, what happens when you have periodic signals like sinusoids or other periodic signals. When we have this kind of signals, what will happen? In that case, integral control will be useless by itself, because integral control can only give constant output for zero error, zero input. For zero input, it can only produce a constant output because it accumulated some number until now. Let's say it reaches to 45. Okay, when you give zero input, it keeps giving you 45, because it accumulated 45. Constant output. But in this case, when the input is zero, you don't want just constant output. You want a certain periodic signal input to the system, so that again you have a periodic signal output. Let's say a motor, or I don't know, any system. Let's say, for example, we work with a Peltier system. Peltier means like you give voltage to it and it can heat up or cool down. For example, if you give negative number, for example, it cools down like a refrigerator. Peltier is something like this. So if you give positive input, it heats up. So if you want a certain shape of temperature signal at the output, for example, they talk about PCR systems, right? PCR, I think. And this virus, that for detection of virus, for example, they need to multiply the DNA, I think. So to be able to do it, you need to give a certain temperature for a certain time, another temperature, certain time, again low temperature, again middle temperature, again high temperature. So you keep repeating this temperature action on the sample. So it multiplies its DNA, I think. So after that, you can measure it. So to be able to have this temperature signal here, so you need a certain electrical signal, of course, here. But because of the dynamics, because of the delays, you need to give different electrical signal. For example, you need to give maybe very high signal in the beginning so that it heats up rapidly. So this is just an example. This can be any system, any dynamical system. So when you want a certain signal output, so you need to inject, you need to give to input a certain signal. Like in a car, for example, you want 100 kilometers per hour. So the gas pedal at that time on that road conditions should be, let's say, 45 degrees for 100 kilometers per hour. But for different road conditions, or there is a wind coming from behind, maybe you are going uphill or something, then you need to give 55 degrees, for example, to get the same 100 kilometers per hour. So you need to find this input, I mean, for that conditions for at that time. So even for a single number, this is difficult. So to have a certain signal output at the output, to find this input signal is much more difficult. actually. Because what shape, what kind of signal should I give here so that at the end, my signal at the output should be looking like this? So this is a difficult problem, especially if, the plant is very nonlinear or has lots of disturbances around. How can we do this? How can we give this certain signal here so that we have a good result? Good result means what? For example, I want this kind of signal here. Output is same signal, let's say. I achieved my goal. I did my best. So I wanted this signal in the beginning. I obtained that signal at the end. So same signal obtained. This is a perfect achievement. There's nothing better than this. You want this, you get this. If you get this, error will be 0. Again, like before. So you want this signal here, you want that signal at the output, same signal. So error is 0. If error is 0, if there's a proportional controller or something here, it will give 0 output. If you have neural net, artificial intelligence, maybe, of course, it's a different story. But if you give this here fuzzy control or something, it cannot do anything. Totally useless. Because for 0 input, what can it produce? Nothing. Because it doesn't know the reference signal at all. It just knows the input. 0 input. So totally useless. So what do we need? We need a certain signal producer such that even for 0 input, it will produce a signal for you. If you can have such a device, that's good. Now you can use it. So that's the main problem in this kind of systems, when you have a periodic reference, or maybe you have certain reference, but you have a periodic disturbance. That's maybe also possible. For example, vibration control systems. Something is vibrating you, but you don't want to vibrate. Let's say you have a delicate machine, shouldn't be vibrated. Maybe you are in a car, there is a constant vibration under the tire, so you don't want to vibrate. So vibration control. In that case, a reference level is 0 maybe, but there is a big disturbance, periodic disturbance. So you need to again inject a periodic signal here so that it compensates the disturbance and you get what you want. Or both can be, of course, possible. Reference may be a signal. There is also a disturbance signal, assuming same period. Then you need to have a certain input to this system so that output is equal to the reference. In that case, error will be 0. Even for 0 input, this signal producer needs to work and gives you the actual necessary input signal. Is this possible? Yes, this is possible using, as I mentioned, repetitive control or internal model control. Let me try to draw something here. So internal model control is something like this. Linear counterpart of integral control. So in integral control, what did we have? 1 over S. Even the input is 0, it can produce non-zero output. 1 over S is like a memory. It's like a integral control, running integral control. It takes the integral. This one, by the way, this thing is in the imaginary plane. It has a pole at 0, S equals 0. So even if 0 input, it can produce a certain value output. Impulse response, for example, step here. For this one, we have in the complex domain, we have poles here, j omega and minus j omega. So what does this do? Even if you give 0 input, for example, impulse response with an initial condition and 0 input, it produces a sinusoidal signal. It has two initial values. One is magnitude, other one is phase. So, but for this one, there is only one initial condition because it's first degree system. This is second degree differential equation. So in that case, we have two initial condition values. One is related to frequency, or for example, the other one is the phase. So if you give two values, you can find this sinusoid. So the good thing about this, even if input is 0, it produces output. So when you have 1 over S square plus omega square here, it will be direct counterpart of this integral control. So this is good because this is exact replication of integral control for the sinusoid case. So this is producing only one sinusoid, one frequency. But of course, you can have S square plus 4 omega squared. That means 2 omega squared. So second harmonic. So you can have many harmonics here. Other harmonics. You can also add it to this system. 1 over S squared plus 4 omega squared. Something like, of course, it's not 1. There should be some number here. For example, 2 plus 5s. Something like this is possible. So using these things in parallel, for example, first harmonic, second harmonic, third harmonic. So you can have the input here. Input is going to here like this. So these are added together. So when you add all these harmonics together, you can have so-called internal model control. One of them is 1 over S squared plus omega squared, 1 over S squared plus 4 omega squared, like 9 omega squared. You can, of course, add as much as you need here. So then you can have this kind of control. I don't know if I have it here, but let me check. References, no. So I wanted to show you a paper, but I couldn't find right now. Let me check now. So there are some power electronics applications, for example, are done like this. This is also a good method, but to come up with these values or designing this system may be difficult. I mean, especially, I mean, for engineers, this may be difficult because engineers wants to plug in a certain controller here, maybe adjust a few parameters, and they want to be done. That's enough. So for them, I mean, just using a KI parameter, maybe adjusting it a little bit, and there are also some methods for it. It's very easy. But for this one, you need to know system model, and you need to make sure your system is stable. You need to spend a lot of time here. And you don't know if it will be working or not. So IMC is like this. Another alternative is repetitive control. You can see papers, books about this. And I'm just giving you a very abstract information here. So in a repetitive control, they use delay. So you have delay here. So to represent delay, you can use discrete time delay like this. Discrete time. So z to the -1, as you know, is one sample delay, z to the -1 in discrete time, or in continuous time, Laplace transform e to the -s td, st, td, whatever. So this thing is continuous time delay. This is discrete time counterpart of it. So you have delay here. So of course we are doing everything in discrete time. Why? Because I mean we can do analog systems also, like operational amplifiers, capacitors, inductors, analog computer, like this kind of things we can do. But today's technology, in today's technology, digital systems are very common, very cheap, very available. Discrete time, I mean digital systems are much more useful. Because in analog, you have lots of noise coming in, and to design it is difficult, you cannot do much. But in discrete time, as a program, computer program or microcontroller program, you can do whatever you want. For example, I don't know, you want, let's say, y equals sine of u. I don't know. Or u squared, for example. Something like this. I mean, to be able to do this using operational amplifiers or something, diodes or nonlinear devices, transistors, is very difficult. Almost impossible. But to be able to do this in a microcontroller system, digital system, is very easy. So all you need to do is get the input, get u. I mean, of course, I am writing a very pseudo program here. I mean, just a sample, very simplified program. So something like this is like a 3-line kind of program. So you need to repeat it, repeat this until what? Until 0. So it can continue continuously, whatever. So until 0, yes. So it will get the input analog digital converter. So it will calculate this number digitally, not an analog way. U is like a value stored in bytes, so like a real number. Of course, it has a certain representation bits. So you will take its square. So you will do it mathematically in the microcontroller. So you will calculate this y, and you will give this y to the output, to the digital analog converter. So at the output pin, you will get this number. So this will be a certain box. So you will give u here, you get y as the output. That's it. But to be able to do this in analog way, analog circuit, impossible. For example, maybe you can say, I did this, but if it is like sine u squared or something, so everything starts from the beginning, so you need to take it to the trash and you need to do a new circuit. But in computer program, it's very easy. I mean, all you need to do is change this to sine u. It will take only a few minutes for you. That's it. You can easily change it. So digital systems, much more easier and available. So you do all these things in digital systems. So that's why I use z to the minus m. So this capital M sample delay. So you do something like this. I am doing simple way. So you have this delay. So you get a positive feedback here onto itself. So it's something like this. So when you have input here, output here, so what does this do? If everything is stabilized, even if this input is 0, because of this memory, not a single memory like integral control, it has a, like integral control, it will have a single memory, but in this case, since this is a delay line, like a delay line, so it has many numbers in it. So even if the input is 0, it will have an output and it will be fed back to the input again. So it will keep repeating same signal, whatever that signal is. So it will keep repeating this signal, this thing. This thing can produce this signal. If the input here, I mean, if the period of this signal is here inside of the memory, so it will keep repeating it, So you can, of course, you can shape this up by, I mean, changing this. You can change this input so that you have zero error. When you have zero error, it will keep repeating the signal, and at the end, your system will work perfectly. Error will be zero. It will produce the signal for you. So this thing can produce a certain periodic signal. That's possible. This is called repetitive control. The other one was internal model control. So it was like that. So let's continue. These are the available methods so far for this problem. So our method is a little bit different than these things. So in this case, we offer a totally different approach. So in this case, the signal is actually dispersed to its harmonic components. So like Fourier series coefficients, like in Fourier series, I mean, you know, there's Fourier series of a periodic signal, the zeroth harmonic like DC signal. I mean, first harmonic is like sinusoid with a certain amplitude and phase. You can also think of it like cosine plus sine kind of thing also. So second harmonic, third harmonic was like this. So instead of the actual real value, why don't we look, consider, analyze, whatever, the corresponding harmonic components of the signal? Like doing the, I mean, you have a prism, let's say, you have light coming in, but you don't know what kind of colors in it. So let's first find the colors inside. For example, for red, that much, for yellow, that much, for example. And then you use these signals independently of each other, maybe like a, I mean, using like cross calculations like this, and then you obtain certain harmonic outputs, let's say. And then you can combine these lights with different colors, again, into a certain light output, let's say. So here, what do we do? Instead of processing the real-time signal itself, we analyze the input signal and treat all the harmonics differently and come up with the output. Something like this. This idea is something like this. So what do? We have so-called harmonic disperser. Last time we talked about this. So we said that this operation is actually taking the sinusoidal component out of xt. So you have a certain signal, periodic signal here. So when you multiply it with cosine omega t, or cosine h omega t, sine h omega t, you are actually taking the cosine and sine components of that signal. Or in combination, if you use like complex sinusoid, e to the minus jh omega t, or tau here. So you are taking that frequency component out of the xt. So when you have averaging using integral over one period, averaging, so in that case, all the other frequency components will vanish. It will be 0 because cosine t times cosine 2t, for example, when you multiply and take the average, it will become 0. Only cosine t times cosine t will give you a certain average value, because cosine square is a positive number. It will have a certain average. But cosine t times cosine 2t, cosine 5t, whatever, there will be positive and negative sign symmetrical. So when you take the average, it will be 0. So they are orthogonal of each other. They are called like this. So these orthogonal signals. So different harmonics will cancel each other. Only that harmonic will come out. So this is a very good idea. So of course Fourier did this. It's a wonderful job. That's why it's called Fourier series. So it automatically gets out the harmonic values. So of course these are constant numbers, complex numbers, except the DC value, because when H is the harmonic component here, H is like 0 is the DC component, H is 1 is first harmonic, H2 is like cosine 2 omega t, second harmonic, H3 is something like this. So, but when H is 0, there is no complex term, just the average of the function. So because this is 1, this thing, so average. So x0 means average, this one. I use this kind of like less than or greater than, like a certain like triangular kind of parentheses here. I use this kind of notation. So this represents the harmonics, numbers, for a certain time. So at that certain time, where do we look? We look for the last period, from current time t back to t minus capital T. Capital T is our full period. Omega is our angular frequency. So angular frequency means what it means, how many angles, how much angles in 1 second. Angle is of course in radians, we measure it in radians. So how much radians per second? For example, in 1 second, 2 pi radians. What does this mean? In one second, 2 pi radians. It means like 2 pi radians means 1 full circle, 1 full 360-degree angle, right? So in 1 second, 2 pi radians means 1 rotation per second. So in that case, capital T will be 1 second. Of course, there is also F. F is frequency. F is like 1 over capital T. So F will be 1 hertz, for example. If 4 pi, for example, in every second 4 pi radians. 4 pi means like 1 full, 1 more full, like 4 pi, like 720 degrees, like 2 rotations. So 4 pi radians per second. So what does this mean? 2 rotations per second. So 2 hertz. In that case, capital T would be 0.5 seconds because 2 rotations per second. So in that case, omega is 2 pi over capital T. F is 1 over capital T. Or omega equals to 2 pi f. 2 pi f. So something like this. Capital T is our period. Omega is like this, angular frequency. T is our time. Tau, of course, I use different variable here. Normally, I should use maybe T here. But I also use T here because it says this integral should be from T minus capital T until T, current time. So this is our limits. But this is our dummy variable. Tau is our dummy variable, is working in this range, adding up all these numbers. So it's integral. Of course, there is a discrete time version of this also. We can come back to this point also. So this is it. This is harmonic dispersion. So it is producing this vector for you. So input is a normal signal input. Output is like a vector, constant vector, but for a certain time. For different time, different vector output. For different time, again, different vector output. So actually, this is changing with time, of course. But this is also changing. The output also may change with time. But if you have a certain signal, periodic signal, not changing, periodic signal, my not changing means, of course, it's changing. But its period shape is not changing. It's like repeating whatever it is without change. It's like repeating. So this, for this kind of periodic signal, do you know, for this one, or for that one, or for that one, I will obtain the same number, same output, because the input is same. But not only that, even here in the middle, let's say in here, in the middle, here, you are here, let's say time. Time is here, let's say T right now. Even for in the middle, if you take this part, if you run this integral, again you will find exactly the same number. Why? Because time reference is always showing the 0 time. Time reference is always this time reference, tau. Here, this thing is only referenced at 0. So even if, believe it or not, you can try, by the way, even in the middle, even here, even wherever you are, since time reference is here, it's not changing. It's always giving you same number. This thing is a little bit different than convolution. In convolution, linear systems, because in linear systems, convolution is very crucial, very important, most important thing, of course, because you have a signal coming in, input, and you have an impulse response of the system. Let's say you have impulse response like this. So you have convolution of these two things to find the output. So when you do convolution, you take this like flipped version and you move it wherever you want, and there you move it there like flipped version. You multiply and add, integrate all these things and find the output at that point. So at the end, output will be like this maybe. So you move this here, again multiply, multiply. In that case, you are moving this signal. But in this thing, things are a little bit different. You keep the signal here. So what do you do? Let me erase here. So in this case, you have a certain signal, e to the e to the j omega t, like this. I'm only giving you the real part or imaginary part, doesn't matter. So you have a certain signal here. So it's repeating itself, let's say, repeating itself. So when you multiply, even if you do here, or even if you do here, same things are multiplied with same things. So even if you do the integral here, or here, or here, exact same output, exact same result occurs. Because same reference is same, is reference things are coming to the same value all the time. So when you multiply, even if you do here, 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 you get exactly same output. So what does this mean? It means that when you have a periodic signal, this output will be constant output for each time. That's a good thing. So harmonic disperser is something like this. Of course, if the signal is changing a little bit, of course the output will be also changing. This output, of course, this is a complex output, but this also will change if the signal shape is changing. But if signal shape is same, it's keep repeating. So wherever time you are, this produces like a DC constant output. So harmonic disperser is something like this. Harmonic assembler is just the opposite operation. So in this case, you give the harmonics to this assembler, and it assembles like this thing. So it combines all these harmonics and give you the output, real-time output signal. This is Fourier synthesis equation. So just the opposite of analysis equation. So in this case, it combines all the harmonics. Of course, it may need negative harmonics also, because in FFT or Fourier series, you have negative frequencies, positive frequencies, actually. So they are conjugate of each other. So since we are dealing with only real-time signals in real life, so X is real. In that case, negative parts will be only conjugate of the positive parts. So in that case, you can also simplify this. You don't have negative harmonics. You just need positive harmonics, including 0. So that would be enough. Because, for example, for -1, this would be conjugate of +1 value. That's it. So harmonic assembler is just assembles all these things. Again, using these values, it recombines it with cosine and sine signal and adds them up and comes up again as signal, the same signal. For example, when you have this harmonics and again put it to an assembler, and again at the end you will obtain same signal. Of course, if you have different harmonics, you will have different outputs. But if you keep giving you same harmonics, or you will have here certain periodic signal. Keep repeating same shape, periods, something like that. So this is assembler. So in harmonic control arrays, what do we do? In harmonic control arrays, we have first this harmonic disperser. So we have real-time error signal coming in. We disperse it to the harmonics. So we have harmonics numbers available here. So we treat each harmonic independently. For example, zeroth harmonic is like DC value. First harmonic is like the omega t component, something like this. So for each harmonic, we have independently running controllers. That's good, because we are not working with the actual real-time signal. We are working with harmonic signal, like taking out from the signal. Is supposed to be a constant signal if it is periodic, really periodic. But if it doesn't have to periodic, of course, because it may be changing a little bit to come up with the correct solution, correct periodic signal. To construct that signal, of course, it will change. So during that time, of course, its harmonic values are not constant. They are also changing a little bit. But this time it's like a DC signal, because from 0 maybe they will go to a certain DC value, although complex DC value this time. So it will come to that value, and when it comes to that value, again we use here an integral control. When we have integral of this coming in error signal, so even error is 0 at the end, this integral, like a memory, will repeat a certain number. It will keep giving you a certain DC, certain number, complex number, by the way. So that complex number will be multiplied with Ki value. Again, complex maybe. And then if you have a proportional controller part, also you can add that up. So at the end, you have a complex number for each harmonic. This is a vector now. This is matrices actually, but this is diagonal matrices. For that means for each harmonic, we have a certain Ki and Kp. So each harmonic affects that harmonic. For example, second harmonic only affects second harmonic. Something like this. So we don't have this criss-cross type of thing. We don't have it right now. We just have like this harmonic affects this harmonic affects that, this harmonic. Why? Because in normally, especially for linear systems, linear system doesn't change frequency. For example, if you shake a linear system with a certain sinusoid, only output will be only at that frequency. It will not change. But if it's nonlinear, maybe you will need this crossing elements also. So in that case, this matrix may be full matrix, but in the, right now we are using it like a diagonal matrix, this thing. So this is a vector. Vector is multiplied with this diagonal matrix, so each harmonic component is multiplied with a certain number at the diagonal. And if you want, you can add this proportional part also. Again, this is a vector, this is a matrix. And at the end, you have a vector output, U. And that is the harmonic of the output signal. So you obtain this. This is dispersion of U, actually. This is, you can read this as dispersion of U, something like this. So you obtain this. From this, using an assembler, it is easy to obtain the real-time U signal, U. So you obtain that, and that's it. So you have this kind of system. Actually, you can have R and Y separately also, but like in unitary feedback control, you can combine this like this. I mean, R and Y is subtracted and obtained an error, and then for error we have a disperser. But this is more general. So after that, after having U, dispersed U, you can have normal U signal calculated using assembler operation and inject it to the plant. So you give this signal to plant and obtain an output. Again, you fed this back, and again this adjusted more. And at the end, what happens? At the end, if everything is stable, error will go to 0. When error goes to 0, this will be totally 0 vector. So 0 vector times 0 kp will be 0. This is like totally useless at that time again. But this part, because of the integral part, even if the input is 0 vector, it will give a certain output vector here. For each harmonic integral will produce a certain complex value, like a memory. So this will be a vector, certain compensating vector. So then this vector is converted back to time domain like a certain signal. That signal is actually doing what it needs to do here. So this signal producer, and this is our harmonic control array. So even if for 0 input, it will give a certain signal for you, compensating signal, so that for this signal, plant behaves like whatever needs to behave, like the reference. So same reference will be obtained at the output. So the error will be again 0. Again, 0 will produce this. Because of the memory, it will produce the signal. The signal will be injected and still, so it will run as desired. So this is the plan. So this is our method, actually. There's an example here. I can talk about this, and today, actually, I will talk about how to simulate this in MATLAB. So I will show you how to do this also today, and how to discretize these operations, because these are normally continuous time. We cannot work in continuous time, especially for this kind of calculation, because in that case there are complex operations, and even square, sine kind of things cannot be done in analog with analog circuits. I mean, this is totally impossible to do in analog computation. So of course we need to do this in digital. Using digital systems, we can only do these things. We don't have any other choice. So of course we will do this in digital, like a program in MATLAB, or as a C program. We can write this easily. So we will also talk about that. So if you want, let's take a break here for 10 minutes. So we will come back at 10:20, okay? See you in 10 minutes. So, yes, let's continue to our presentation here. Okay, this is the main model for a simplified harmonic control array block diagram. So in that case, we have error here we have disperser for the error. So dispersed version of the error here. That means the harmonic values like a vector. So each harmonic is treated independently. So using this PI control. So at the end they combine together and as a vector, harmonic vector input, dispersed U, and then they convert it back to time domain. Something like this. So this is let's do a little application here. I mean, let me see this. Yeah, this plant. This plant. Let's use a typical system model here. So what will happen? So let's see. So this is a typical system model actually. This is a like a delay here, TD, time delay, disturbance signal, and a dynamic first order, simple dynamic here, A over S plus A. That means when S is 0, this gain is 1. That means DC gain of this system is 1. So something like this. So reference and disturbance signals. Reference signal is like this. So how can I find the harmonics of these signals? Like this, 2.7 is the average value. Actually, once you come up these numbers, you can draw this signal using like this, 2.7 plus -1 is real number, -1 times cosine omega t, like 0.5j is like sine, so 0.5 times sine 2 omega t. By the way, omega is here, period is 1, as you see. So omega would be 2 pi over capital T. Capital T is 1, so omega is 2 pi here, by the way. So reference signal is like this. Disturbance signal is like a random signal, very huge as compared to this, like very strong, I mean, signal. So in that case, disturbance is unknown. We don't know disturbance signal. So it's coming in. So it's changing things here. So we want to keep Y like this. So how can we inject a certain signal here so that we can obtain that reference signal here, even if there is disturbance, a delay, and a dynamical system? So that's the problem. So if we use this harmonic control array system here, this A is, by the way, 1, something like this. So without delay, let's say, for example, there is no delay right now. In this case, if you choose, all you need to do is choosing the Kp and Ki numbers. As I said, it's a diagonal matrix because we don't have like crossing harmonic components, like only DC affects DC, first harmonic affects first harmonic, like this, like 10 is the first harmonic gain, 15 is the second harmonic gain for proportional gain, and these are the integral gains. These are just very easily tried and found values. So for these are, by the way, real numbers, but it doesn't have to be real. These can be complex numbers also, by the way. So for this choice, this is the result. So how did we come up with this thing? by simulating the system in MATLAB. We will come back to this point later. How did we do this in simulation? So, but this is the result. So in the beginning, let's say we have a certain reference signal. So our system tries to mimic that, and at the end, as you see, it produces same signal for you. So error becomes 0. Even if there is disturbance, delay, there is no delay actually in this case, but even if there is a big disturbance, it automatically constructs a certain input signal so that output is equal to reference, so that error is 0. So how does it do it? I mean, if we look at the individual harmonics of the signals at the output, you can obtain like this. So of course, when you talk about harmonics, they are complex numbers, cosine and sine numbers, something like this. So we can look at the real part and imaginary part. So actually we have two signals when we talk about a complex signal. You have real part, imaginary part. So if we look at this, real parts needs to go to 2.7. Actually, for zeroth harmonic DC, we have only real. We don't have imaginary for H0. So for H1, it needs to go to -1, -1. Why? Because our reference was like this. So second harmonic should be -1. Sorry, first harmonic. Second harmonic should be 0.5J, something like this. So second harmonic, real part is 0, imaginary part is 0.5. So this means 0.5J. So does it really go there? Red one. Yes, 0.5. It goes to 0.5. Like a PI control. Because in PI control, in normal PI control, it has an overshoot and it goes like this. So similarly, of course, there are many harmonics, many signals around working together. Of course, we have a noisy kind of thing, but at the end, this second harmonic is supposed to go to 0.5, and it goes to 0.5. How does it do it? Using an integral control, because integral control produces this certain output. So, I mean, this goes to the input of the system, and at the output of the system, you get 0.5 output. So, for example, fourth harmonic needs to go to -0.1J. Yes, it goes to -0.1J, for example, this one. So the DC real part needs to go to 0. Yes, it goes to 0, for example. Something like this. So we get what we want. I mean, we can also see it from the signal, because these are harmonics, harmonic signals. And if you combine those signals, although they are going to DC, certain value, at the end they produce this periodic signal at the output. So when they go to a certain level, actually they are in total produce a certain signal, certain periodic signal, and that periodic signal is equal to the reference signal, producing 0 error. So that's good. It already done it. By the way, when you combine all these signals together, this goes to a certain value, this produced signal, input signal, control signal, whatever, is a certain periodic signal at the end. And in the beginning, it's changing a little bit, because it's constructing slowly. Every integrator works and tries to come up with a certain correct value, complex certain value. So after that, it produces a certain signal. So this signal actually, at the end, becomes this signal after the system. So you inject that control signal to here, and at the end, you obtain this desired signal at the end when you inject this signal to the system input. So this is actually automatically constructed. What you need to do, you just need to come up with, like in integral control, these numbers. That's it. When you have these numbers, that's it. This is your job. So control engineer's job here is just to select these numbers. So as easy as this one. So it's not like repetitive control or internal model control, and lots of modeling, lots of calculations. No, you have a ready algorithm. All you need to do, like in PI control, it's used more than 99% in the world industrial systems. I mean, all you need to do is come up with these gains. That's it. So you can use, of course, as many as you want here. This will be only limited by your calculation power system, something like that. So you obtain that. How about for a delayed system? If you have a considerable delay here, because the period is 1, so 10% is delay, is actually very high delay actually for this system. So in this case, if you choose these numbers, of course you can ask how do we come up with these optimum gains is another problem. But when you come up with these numbers, as you see, it automatically controls the system and error goes to 0, like here. So not only for periodic inputs, for DC inputs, you have also solution here. Maybe you will say, if constant reference, why are we using this harmonic control arrays? Because normal integral control is also available and maybe enough. But actually it's not enough, because we have disturbance here. Don't forget, we have a huge disturbance. So that disturbance is affecting our system. Even if we want a constant reference here, there is a disturbance coming in. So that's why we have to inject a periodic signal to the input. Even if our output and reference is constant at 10, for example. And by the way, DC values can be easily represented with this vector. DC component is 10, so it's 10 average. But all the rest of the harmonics are 0. So that means there is no fluctuations, there is no signal sines or cosines, just the DC value. So DC values represented like this in a harmonic case. So in this case, our reference is like this. All you need to do is changing reference. I mean, you keep same KP and KI. You don't have to change anything. Just you need to change your reference here, instead of this, you just choose reference like this, nothing else. So in real world or simulation, doesn't matter. All you need to do, change reference, so it will automatically produce this constant output for you, like it did for this. So it automatically produces this reference for you. But since there is disturbance coming, input to the system, input signal to be injected into the system should be a periodic signal. Like, as you see, it's a very complex periodic signal here injected to the system, so that you can obtain a certain constant value at the output. So this may be an example of vibration control, for example. So you want to keep your system, your mechanical system, for example, you don't want it to shake, but there is something is shaking at a certain frequency, periodic signal. So something is changing your system. Normally it will oscillate with the same frequencies, of course, with different amplitude, of course, and phase. But in this case, you are injecting as compensating signal, injecting to the system in such a way that at the end, even if this is shaking, this is not shaking. This is at a certain level. It's not shaking. It's a certain output. It's not affected by the disturbance at all. And it does a pretty good job here, as you see. So in repetitive control, for example, and also in others, because of the delay, you introduce an artificial delay into the feedback loop. This is a little bit dangerous because delay makes things unstable very easily. Of course, if your model matches perfectly, and if you calculated everything, theoretically, it can work for that particular model. But if your model changes, especially for repetitive control, this may easily make your system unstable. So let's see if there's a similar situation for harmonic control arrays. So if we use this system again, if you look at the error, even if you choose A1, A 0.7 or 1.3, by the way, A was the system dynamic parameter here, A. So even if A changes, same controller here, same controller produces again 0 output. So it's very flexible system. So this is good. Another example is an unstable system with delay. In this case, you have unstable system and you have delay. So this is a difficult problem because control is very crucial here. If you don't have a good control, it will be, easily become unstable because it's already unstable. But also there is a delay. You don't have knowledge of the output right away. After 0.1 seconds, you can only, or let me see. Let me check that. TD is 0.1 seconds actually. Yes. So in this case, Yes, 0.1 seconds. So you have like delay for the, you don't have knowledge of the output right away. And also there is a disturbance. That's another headache. This is unstable. So there are three things altogether. Bad things are in the system. So even for this situation, using this simple choice of parameters, I just tried them like in 5 minutes, or I don't know, 10 minutes, you can obtain maybe this values by just adjusting the numbers, but it's not always easy like this. There's a certain method. There should be a certain method to come up with these values, of course. So at the end, as you see, you get again 0 error. So it automatically produces the reference signal at the output. So there is another actual hands-on application of this method. We use the motor and the data acquisition and control system, and we compared the results with PI and internal model control. As you have higher and higher order harmonic control arrays, you have smaller and smaller errors actually. So as you increase the harmonic numbers, all you need to do is to come up with this number. So designing control is also maybe very easy for this method. So you don't have to use a complicated method here. So especially for engineers in the industry, this method may be very easy to use because you have already a certain program. All you need to do is to come up with this gains. That's it. So that's why it may be useful. So I think that's it for this presentation. So now I will talk about how to obtain these, how to simulate these things. So for that, let me see. Sorry. So here, yes, in the web page, actually you see these application software programs. So when you click here, procs folder will be downloaded, and from here, let me see. So you have these programs available for you. So all these programs are available, so you can take a look at this program. Of course, there's a C program also, but if you want to implement this in a microcontroller, you can see it. So these programs in 2005 is the original papers program. So we have this paper here. So like we did, this is our reference, disturbance, and these are the figures we already covered in the presentation. So these are the results. So these figures are obtained using these programs here. Programs. So let's see. So in this case, we have this original program. This is the original program here. So this is Turkish a little bit, some of the parts, but this program anyway. So harmonic number. Capital H is the number of harmonics, I mean. Like we did in the beginning. Like here, capital H. Capital H, but of course, if we count the DC value also, capital H plus 1. So size of this vector will be capital H plus 1, including DC. So we go up to capital H components here. So that's that. So we have reference input like we did again here. Reference is this vector. So reference is that vector. Let me see if it is same. Yes, it's same here. Of course, in MATLAB, you can use I or J. Let me see. Yes, J or I. Doesn't matter. So we have this reference. Disturbance is, as in the presentation, is here. So by the way, we have 4 harmonics. That means 5 elements, including the DC, 1, 2, 3, 4, 5. Yes. So this is DC component. This must be a real number, by the way. This must be a real number. This thing is complex numbers, can be complex numbers. A is the system parameter, by the way, this A. That means this system. If it is -1 over S -1. So it will be a unstable system here. T is the capital T period. Omega is like 2 pi over capital T. TA is the sampling period. So of course, this is a digital system, discrete time system. So we have to calculate things in discrete manner because we have digital systems, they work in discrete time. We cannot have infinitely fast system, so we cannot take this 0, I mean calculate like an analog system, impossible. So we have to choose a relatively small enough time unit for calculating our outputs for each sampling point. So the sampling time, we have 1 second period. So 0.01 means like every period we will calculate 100 numbers. That may be enough. If it's not enough, we can make it like 0.001 if you want. Or you can, yeah, that's 100 is actually maybe enough for this system. Our time vector, this is just for simulation, something like this. 5 capital T is like, we are going 5 periods here. So our time vector is like this. So for calculating the real time signal out of harmonic components, we do like this. Okay, first of all, how can you understand this? It's a little bit complicated. Maybe you can think of it, but it's mainly like this. E to the minus j omega ht is our integral part. This thing. So we are trying to find this. Sorry. We are trying to do this, I think. Let me see. Yes. Let me make sure. Yes, that's that thing. So this thing, we are assembler part. So we have harmonic components like this. Let's say we have this thing, harmonics available. So how can you come up with a signal? So how can we find this signal? So actually here, this thing. So let me go back to this. Yes. So we have harmonics, positive side, positive harmonics, and negative harmonics. Well, negative harmonics are conjugate of it. So we just need positive harmonics. That's enough. So we need to multiply with e to the j h omega t. So e to the j omega h t. But I take it like this. Do you know what this is? T is a vector, like a row vector all the times. This thing is a column vector. So when you multiply this and this, I know this is a very big operation. Normally you should do it with 4 loops, 2 for loops or something like this. To, calculate this, you need like 4 loops or something. For every t, you need to multiply this. So you need, but in MATLAB, of course, if you can do it with a single command, ready command like matrices, vectors, it's much faster and much easier. So when you multiply this, this is like a matrix. One of them is row on the right side. On the left side is like 0 to h, because we need to multiply h and t. Also omega and j omega. Yes. We have exponent of this. Yes, we have exponent of this. But now this is a matrix. For each h and each t, we have a value. So t is like on the row. T is in the column and h is in the row, something like this. So you have very huge matrix here. You multiply this with harmonic vector. This thing. This is a harmonic vector. Since this is a matrix, like each row representing harmonic, when you multiply matrix with a row, with a reference harmonic vector, but it's transpose, okay? You have a matrix with a row vector multiplied together, so it will, of course, do normal multiplication, matrix multiplication, but at the end, it will also do multiplication and adding together, because row vector and matrix when multiplied is like multiplication plus adding, like we have here. So transpose of R. Why I didn't use like this? Transpose of R in MATLAB is like this actually, but I didn't use this. I used transpose. Why? Because when you have R like this, let me try in MATLAB. So when you have R vector like this, well, this is a vector, R prime is a row vector this time, of course, transpose, but this complex parts are conjugated when you do this in MATLAB. Because this is not a transpose. This is Hermitian transpose in MATLAB. Normally, Hermitian transpose is much better and much useful everywhere. That's why they use probably this Hermitian transpose. But I don't want Hermitian transpose. I want normal transpose and multiplication. I don't want to change the R values. But if you have transpose of R, in this case, it doesn't do Hermitian operation, I mean conjugate. So it just transpose whatever the value, it just vector, row vector, column vector is converted to a row vector using same numbers, of course. That's it. So there is a little bit difference like this in MATLAB. So that's why I use transpose here, multiply it like this. So I already cover what? I already cover 0 to H components, positive ones. But I need to do negative parts also. Of course, actually, I can do this plus I can take the real part of this and multiply with 2 or something. I mean, but instead, I use the negative parts also. In that case, I use negative frequencies. I use conjugate also here because there will be conjugate operation needed for negative ones. So this is normal, like Hermitian transpose. I can also do that. So at the end, I combine this. This is supposed to be a real number at the end. Real number. But actually, I don't need to calculate this, as I said, because it will be just conjugate of this part. But I did like this for this program. At the end, this should be a real number. But because of little calculation errors, there can be a little bit imaginary parts remaining also. That's why to get rid of it, I use also real part of this. So this is one way of doing it. So for disturbance, of course, I use the same thing. So this R now, R represents my real-time signal. So if you plot it for each time, if you plot this, you will be seeing the actual signal having these harmonics. That's it. So let me break here or stop here and run this program and let's see what happens. By the way, in MATLAB, there is a command that perfectly works, but in MATLAB, I mean, documentation or help or something, you cannot find this command name at all. They don't mention to this command, but it perfectly works. What is this command? Stop command. If you write stop, it stops here. Why it stops here? Let me see. Because it doesn't know this command. It doesn't know this command, that's why it stops. So it perfectly does its job, but it's not a real command of MATLAB. So I always use the stop command also. Of course, there are some easier ways, but this is what I choose. So it all, when it stops, I say, oh, okay, it's perfectly worked. So let's see the result. As you see, time was like 5 capital T, so it goes 5 periods. So 1, like 1, 2, 3, 4, 5. So 5 capital T. This was our first signal up to here, up to 1. So this is what? This is our reference, this one. This one. So if you want, for example, you can change this to, I don't know, you can make this 0, for example. Let me see. You can make this 0 and run again. And as you see, average value is now 0. Okay, something like that. So for example, instead of 0, for example, you can make this 1J, something like, let's see what happens. So totally different signal. I don't know. Yeah. For example, you can make this to, I don't know, maybe you can make this to, instead of 2, you can make it normal 2 instead of 0.2. See, it's a different signal. Something like this. So that's normal one is this one. So these are the harmonics. So this is in one shot, in one line, calculates what? Calculates this in one line of code. That's it, this thing. And not only one T, whole T, I mean, from beginning to end, it calculates this thing. This only one command in MATLAB is very useful in that sense. In one command, you can do many things. So you drove this here, and that's it. And after that, what do we do? Let me get rid of this top here. So after that, I calculate a number of samples for each period. So our time, again, like this. So this is actually for one full period, something like this. So there are, of course, lots of details here. I do some initializations. I use my KP and KI. This is what? This is probably the system with delay with negative A. So in this case, this thing is, this is for D equals 0 actually. So at the end, of course, these are not important because this is again used here. So this will be the effective one. So let's see. Yes, it's the same thing. Yeah. So when you have these things, these are, by the way, diagonal KP and KI. Let me see. Yes, diagonal matrix, something like this. So every time steps, what do we do? What do we do? That's the important thing. So in the so by the way, I always use normal code instead of Simulink or something, as much as possible, of course. So in this case, my U is calculated first. U, by the way, this is integral part. So to be able to simulate the integral part, you keep adding the input error. So error is actually here is a vector, dispersed values harmonics like a vector. So TA is our sampling period. So this thing simulates the integral. Integral is this. So it's keep accumulating the incoming number with a certain step. So this is our integral of the error. It's multiplied with KI, this one, matrix. KP times E itself, normal error, dispersed error. So by the way, dispersed error will be calculated like before here, but this time we are doing dispersion, just the opposite operation. So in that case, we have e to the minus j omega ht kind of thing. So here we have actually this operation. And something like this. Let me see. Yes. Something like this. So error is calculated like this. Y also calculated, but this is for only seeing the result. We don't have to do this for control purposes. We just need E calculation. So E, integral of E is here. So integral part of the E here. So K pay Ki. So after that, how do you obtain U? Like in normal, like we did here. Similarly, but for each time this time, not for all time. For the particular time, we obtain our real control signal out of this harmonic input. Disturbance at that time is also calculated. This is for simulation purposes. And after that, plant dynamics. So actually, input is coming to our plant here. So we simulate this thing. How can we simulate? Actually, simulating is easy, but this is even easier maybe, because in this case, like derivative of y actually is this. I mean, if you do this operation, actually this means like output actually, let me write it here. Y over U in Laplace domain equals to A over S plus A. So this means that Y dot, I mean, if you think the real time, y times S is Y dot plus A times Y equals to A times U, or Y dot equals to A times U minus Y plus U. So this is the system. So if you know the derivative of the output, you can find the output. How can you do it? So if the derivative is this, then derivative means yk plus 1, let me check, yes, yk plus 1 minus yk, the previous value, over the sampling time represent the derivative approximately, if your capital T is small enough. If not, you can make it smaller. So this thing is here, okay? So now yk plus 1 equals to T times this capital T times the derivative plus yk. So yk plus Ta times whatever the derivative. What is the derivative? A times minus y plus u. A times minus y plus u. But u here, actually, let me see, U is also added an extra term like D. So here, so D. But by the way, U is delayed. Delayed version of U is coming. U is here. Delayed version of U is coming here. So delayed version means like K minus delay. So delay is what? Delay is delay time over sample time. This is the discrete time step number for delay. Now that's it. So this is our simulation in one line again. I mean, this whole total thing is simulated with a single command, single line command. That's it. I mean, sometimes people are using the, simulating everything. Why? Because it's easier. Yes, easier, but you don't know what's going on inside. It's simulating something, but with which step, what kind of method. I mean, of course, you can choose it, but you don't have enough information about it. So you don't have control too much. But in this case, this total thing is simulated as a very simple one line command. That's it. So how about the next values? So our reference value, of course, needs to be used here. We have an initial value. So our reference value is again obtained similarly. Error is actually reference minus, of course, output is our error. And then using these things, we can obtain dispersions similarly. And if we use a for loop for up to whatever, how much period we can go like this. So at the end, we have this simulation, and these are the for drawing figures. That's it. This is our program. So if you run, let's see what happens. So this was our reference, of course. This is composed control signal, figure 5. Let's check. Yes, this is our time. This is our input. That's it. U was this thing, constructed signal. As you see, yes, control signal is like this. So it's very complicated control. So this thing is our actually output signal. As you see in the beginning, it's a little bit trying to match up to the reference signal. And at the end, we have zero error. That's it. These are the actually, yes, output harmonics. So they are going to a certain value, as you see. They are going to a certain value as supposed to be. So how can this be possible? By using an integral control. So integral control automatically adjusts each harmonic component. That's it. So let me see to catch this. So the real parts of y is also going to the correct places, and that's it. At the end, our system output goes to the system output. So that's it. So you can easily, you can also try this actually. So if you want, you can try. So where is my program? Mhm. Yes. So here, if you want, you can try different things. For example, what happens if A is something like positive? But in this case, of course, you need to change the gains. So for A, H, D, yes, this one. For this one, we have, let me see. So for A equals 1, where is the, yes, TD 0.1. So yes, 0. Yes, this one. So we need to take this one actually, not this one. So let me get rid of this, and it will be, this will be effective now. So if you run, yes, we have automatically again controlling things. So if you want, you can change A a little bit. For example, 0. Of course, it may be different. So you can try different things with that this program. So as you see, I mean, yes, a little bit, I mean, looks difficult, but at the end, it's a simple program. So it does everything in one program page. So you can do everything, you can try like this. So this is an initial program. In this case, there is a little bit problem in the calculation time maybe. Actually, we didn't feel it because it's very quick for this case. But in real time, when you calculate all these things with a C program, also may be easy. But when you have very high frequency system, very fast system, calculating all these numbers may be difficult. I mean, it will take lots of time, because at every time you are calculating these values. So every time you calculate, every sample time, you calculate the whole last period. So instead of this, you can sometimes make things easier. So for that, we have actually another paper for you here. I'm sorry. Yeah, maybe let's look at here. There's a paper also, but let's see this implementation guide. So in this case, this is our disperser. So this is our dispersed vector. This is our assembler. By the way, instead of using like negative H, positive H, you can only use this positive part and DC. So if you want, we can immediately try this here. I mean, for example, instead of doing this, let me, if you want, just try here. For example, let me again put a stop here. So let me close all these things for a while. So instead of calculating like this, normally it was calculated normally, yes. But instead, I will use this formula now. What was the formula? Instead of negative components, 2 times the real part of this part, positive things, plus the DC component. This should give you the same answer, same result. In this case, you don't use negative harmonics like conjugate. So you don't have to do this. You just use the positive harmonics. So in this case, so let me do it again. So in this case, I will have, first of all, let me see, only, I don't need this conjugate. Yes, I get rid of this. I multiply this with 2. Yes. So, but I will start this from 1. Yes. 1 to h. Let me check. Where is the thing? Here. So, I will add the DC also, DC part. So how can I add the DC part? So when this is 0, it will be like 1. So transpose of R. So transpose of R, this will be like, let me see. Let me see, transpose of R. Yeah, so this R will actually go from 2 to H, because we will use only that part, okay? So this will be multiplied with this thing. Let me see, this is going H plus 1, sorry, H plus 1, because R is a vector with H is 4, so it goes from 1 to 5. So it normally goes to 1 to 5, but I will use only the higher harmonics, not DC. So I need to add the DC component. Where is that? So only the DC component. Yeah, this one. This is the DC component. So in this case, that DC component only R0, because R0 is the DC component. So instead of calculating it this way, this way, I calculated this way. So it looks more complicated, but actually saves time, because in this case you calculate both sides, negative parts, positive parts, lots of numbers calculate. But in this case, only right hand side calculated. This takes some time. So you multiply with 2, taking real part and 2, and then add the DC part. So let's see if it will produce the same answer. I think that's correct. So let me again try this first, original one. Yeah, original one was like this. So let's see. And by the way, let me hold on this. Let's draw on it. So let me calculate it this way. It is lots of time saving, but actually it's fast in this case, but in some situations maybe. Sorry, R1. Of course, this is because MATLAB starts with 1. R1 means H0, actually R0, zeroth component represents. Yeah, I think that's it. Yes. Let me close this and run. Yes, it obtains exactly same results. So this thing can save time. Instead of negative like things, you don't have to do it. You just use this formula. That's it. So it's easy to use this one. So harmonic control block diagram is like this, like we already seen in the presentation. This is the Ki over S. This means like integral part of the harmonics. This is proportional part. And this is what we do for our control harmonic calculations. Okay, up to here, normal continuous time. Continuous time, but in program, of course, we do discrete time. So instead of this continuous time operation, if we do everything in discrete time, we can do like this. Instead of like this integral, we can do like this. So xt times e to the minus jh omega t, instead of t, we can use k times ts. Ts, capital Ts here is the sampling time, okay? Sampling period. So this is our normal e to the j term. This is our xk samples. And we are taking it from last period. So last period means capital M, by the way. Is it written here? Capital N is, it's written here. So capital N is our number of sample points in one full period. So one full period is time is capital T, sampling time is Ts. So if we divide these numbers, we have number of samples in one full period. So so we go over that period. Of course, we need to add this because we just want one full period, including little n. Current time is here, n is a discrete time. So one full period. So we need to divide this capital N because this is there are capital N numbers here, total. So if we divide it to this, instead of dividing to capital T, average, so we divide it to capital N. Instead of integral, of course, we have a sum operation, so discrete time. So this is the dispersion part. So what is this? This is omega. Instead of omega, actually, you can use 2 pi h omega ts, capital. Omega capital Ts, omega is, by the way, our 2 pi over capital T. So if you multiply this, we obtain 1 over 2 pi over capital N. So you can have this. So omega is 2 pi over capital T. So Ts over capital T is 1 over N. So you can also write like this. So in this case, there is only a capital N parameter, and K is the actually dummy variable here, counting operator. Little n is our time step, and h is our harmonic number. That's it. So you can calculate like this, actually, in discrete time. Actually, we did this. This is nothing different than this operation. Same thing, actually. So, like this. So, we actually, let me see. This is for obtaining UK. Sorry, this one. This one. This one is actually this thing. So, actually, when we do this, when we calculate, we need to calculate this for each little n. So each little n, we need to multiply these two things together, xk with this. So xk, so we calculate for each time step, we need to calculate this. But we do it like this because there is a, let me erase this. So we have a certain signal, like certain signal coming like this, xk, xn, whatever. So we have a certain sinusoid. So each time step, what do? We take the last period, multiply with these two things together and add them up. At the next time step, what do? Again, we take the last period. Again, we take the last, this sinusoid, multiplication. So instead of doing this, because we are doing common operations here, maybe the this leftmost point is not here, but there is also a new point coming in. But the points in the middle are same actually. So at every time we are calculating, multiplying same numbers actually here. So since we do same numbers calculating, we don't have to do it in microprocessor, because doing all these things, especially for past control things, our microcontroller may not be enough to do this. It may be not enough because lots of calculations, sign calculation, multiplication, addition, lots of things, same calculations. So why are we doing same calculations, Simon? This is because the middle ones are same. So what can we do is take out this leftmost entry, get rid of this. Of course, we need to memorize the values. We need to put them into memory, and we need to get rid of this, and we need to add the current one. So remaining here should be same. So instead of this, you know this operation. So we keep the value, middle values. So add the new entry to the system, extract the leftmost entry. So if we do this, instead of doing lots of sine, cosine multiplications with our signal, we can simply use this thing. At every time step now, our calculation burden is much lower. Because in this case, we have capital N multiplications, sinusoid calculations, adding. But in this case, only one sine computation, and also only one multiplication at each step. So this is much more effective. It's seemingly much more effective way of calculating this thing. So in the beginning, we had this operation. Let me see. This operation. Every time step we need to do this, but in discrete time we need to do this. But even we don't have to do this, because in the middle we already calculated. We just add the new coming in one and get rid of the leftmost input, and you can easily calculate like this. So as a final algorithm for this method, you can do like this. You can just calculate the error reference. You know, you can also calculate this using this, as we did here. You know the signal, okay? You can have the signal here. So you know this is given. Yn is coming from the system anyway, so you can calculate the error. So after calculating error, for each harmonic component, you can do this. So for each harmonic component from 0 to capital H, you calculate these numbers by simply adding this thing. So the current error value minus the leftmost current, and one period before the period error value. This thing over capital N, okay, like here, capital N. So this will automatically build up your dispersion vector error. So integral for integral, like we did here for integral. So you keep adding this error dispersion vector, accumulate this, okay? Keep accumulating, keep accumulating. That means what? That means integral of this thing. So this is this. Kp times error dispersion plus Ki times integral of error dispersion. And then finally, once you obtain this error input dispersion, then using this again, this thing, using this thing, you convert vectors to time domain easily like this. That's it. So this is our main algorithm for this method. So is it too much calculation burden? No, because this is easy to do it. Even very fast algorithms. Let's say you have 50 Hertz power electronics application. You need to obtain a AC output, sinusoidal output at the output of your power electronics circuit. So 50 Hertz, there are some harmonics due to nonlinear load. Let's say you can go up to, let's say, 10 harmonics. So 50 Hertz is 500 Hertz. So even 1000 Hertz, 1 kilohertz, so 1 millisecond. So every millisecond, but of course you need to do it, you need to take some samples for each period. So maybe like 1 millisecond is our, let's say, highest harmonic frequency is, let's say, like this 1 kilohertz. So in this case, 1 millisecond is our period for that. So if you want to sample this, you need like, I don't know, maybe 10 microseconds. So every 10 microseconds, you need to calculate this for each harmonic, 10 harmonics, for example. So this is possible. In today's technology, it's very, very possible. In 10 microseconds, you can calculate this 100 times. This is not a big deal. So after that, you can calculate this. So even for fast applications like power electronics, you can go up to 10 harmonics and you can still have a good algorithm. All you need to do is what? All you need to do is decide on this Kp and Ki. That's it. These are the vector. We take it like diagonal anyway. So all you need to do is come up with these optimal gains. That's it. And this is another, of course, subject to how to optimally calculate this Kp and Ki for a given system. So we have a system. So you have either modeling or simulation results of this system. So how do we come up with this optimal Ki and Kp gains? Once we also obtain this Kp and Ki, so we can just run this algorithm on a microcontroller, for example, or in a computer, whatever, and control our system according to our desired reference signal. I think that's it for now. So next week we will continue, but I think that now we need to deal with the case studies. So you need to find a journal paper or any conference paper or a patent application or whatever, any system application, so that you want to control something, either reference or disturbances periodic. So you need to come up with an example like this from either journal, conference, or you can come up with by yourself also. As I said in the chat, maybe you can look for repetitive control or internal model control papers. So we will deal with each of you individually, what you come up with. We will decide on the paper and system, and then we will work on it afterwards, okay? So after this time, we will do case studies. So we will do it together using these programs and other programs. We have also available Simulink models here. You can also use Simulink models, although I don't want too much, but that's okay, you can use it. For example, let me see. So in this Simulink model, let me see. So if you do not want this MATLAB program, you can also do like this. I mean, there's a system here. Y is taken and fed back. If you want, you can put a transport delay here. So you come up with this RD, KP, KI values here. And you can decide on your TS and T, and it automatically calculates the values for you. That's also possible. Let me see. It takes time. Yes, it takes something like this. So you can also use this Simulink model if you want. That's also available in the web page I mentioned. So that's also possible. So you can prefer this if you want. So see you next week. So I am expecting you to find a good working system so that we can prove our method is not less than repetitive control, internal model control, and sometimes even it can be better. That's our aim for the sample application. So see you next week. Bye for now. Thank you very much.